Alright, well I almost forgot to post this video tonight, but luckily I remembered. Please forgive the sound of the washer running over there in the next room. Tonight we're going to take a look at the topic of higher order derivatives. I can't remember what section number this is in our book, but I think it's 3.5, but I can't be sure. But we'll know tomorrow, and I'll have a homework assignment as well on this. Let's suppose we have the function f of x equals 6x cubed plus 2x squared minus 3x plus 1. As we know, we can easily take the derivative of this function using the general power rule. The derivative would be 18x squared plus 4x minus 3. Well, very often in calculus, we're also going to need to take a second derivative. And the notation for the second derivative would be f double prime of x. And as you would guess, the second derivative is simply the derivative of the derivative. In this case, it would be 36x plus 4. Well, if we can take a second derivative, we should be able to take a third derivative. And the notation for the third derivative would be f triple prime of x. And in this case, the third derivative would be 36. And if we can take a third derivative, we can certainly take a fourth derivative. Now, the convention for the notation here is the prime notation generally only goes up to third derivative. As soon as you get beyond third derivative, we tend to put the order of the derivative in parentheses as a superscript. So, let's say you had a 7 here in the parentheses. That would mean find the seventh derivative of f of x. And it's rare, but it is possible, because my calculus book did this. Sometimes they use Roman numerals for the derivative. So the fourth derivative could also be written using Roman numerals. Never quite understood that, though, because sometimes you can get, rather large numbers in there. Doesn't quite look right. Anyway, so this is pretty much the only skill you need to know when it comes to higher order derivatives. Just know how to take the derivative of a derivative and continue the process. Now let's talk a little bit about the Leibniz notation. How would Leibniz notation work for higher order derivatives? So as we know, dy dx simply means the first derivative. If you want to take the second derivative, here's how we write it. So notice here in the numerator that the second order goes between the d and the y, and in the denominator the second order goes after the x. Why it's written that way, I'm not really quite sure, but that's the way it's generally done. So this notation over here, oops, that's a mistake, that should be a 3 right there. But that would be the notation then for the third derivative. Okay. Now why would we even care about higher order derivatives? Well, let's focus on the second derivative for right now. Let's take a look at these two graphs right here. And let's suppose that you're running a company and you're told that, hey, guess what? Your profits are increasing. Well, if you look at both of these graphs, that statement would be true. In each one of these graphs, it is true that your profits are increasing. But I think you would be really concerned about which situation here you had. In this case, your profits are increasing at an increasing rate. In this case, your profits are increasing, but at a decreasing rate. So let's draw some tangent lines on this. Let's say at this point right here, it looks to me like the value of the derivative may be, say, 1/2. And at this point, the value of the derivative may be 1. And so on up the graph. So notice here that your derivative is increasing. Now, if your derivative is increasing, that means that your second derivative will always have a positive value. Looking at the other graph, your profits are increasing, but now they're increasing at a decreasing rate. For example, the slope here, or the value of the derivative here, let's say maybe it's 2. Well, the value of the derivative here is going to be less than 2. Maybe 1, let's say. So in this case, your function is increasing, but what are your derivatives doing? Your derivatives are decreasing. Well, if your derivatives are decreasing, that means that your second derivative is going to be negative. Okay? So a positive second derivative means that your function is increasing at an increasing rate. And a negative second derivative means that your function is increasing but at a decreasing rate. And there's a lot of other nice applications of the second derivative, which we will take a look at in the next few days here. And also a lot of nice applications that we'll see in Chapter 3. So that's all for now. Tomorrow I'll have a homework assignment ready for you on this. And we'll see you then.